Every physical structure reacts to the forces around it. Subjecting a synthetic polymer to a 300% elongation force triggers a rearrangement of its molecular structure. The material adapts to the stress, displacing its internal bonds to survive the load. In mainstream neuroscience, we model the memory of these inputs through chemistry. We look for synaptic weight changes, new proteins, and mechanisms like long-term potentiation. But those electrochemical signals are embedded within a physical matrix of biological tissue. This matters because the human brain is the softest organ in the body, and it is highly viscoelastic. It possesses mechanical properties that dictate how it absorbs, stores, and distributes energy over time. This integral defines viscoelastic stress. It calculates the current stress state of a material based entirely on its history of strain. This math demonstrates that memory is a property of matter itself. In physics, this is known as path dependence. The present state of a system is dictated by the trace of its past states. Biological memory utilizes this physical path dependence, scaling it from microscopic molecular deformations up into the complex networks of the brain. Biological matter exhibits this persistence. When cellular fibers endure mechanical forces, they elongate and slowly relax into a new formation. They do not instantly snap back. They retain the physical history of the stress. The Brain Kinematics Model uses this as a starting point. It proposes that the brain processes information by routing forces across tissue densities with different mechanical histories. Thoughts and episodic recalls are modeled as force flows navigating through these specific biophysical gradients. To decode human memory, we are moving past the computational metaphor of the brain to analyze the mechanical parameters of the tissue itself. We can contrast tissue mechanics with simpler systems. In a purely elastic material, stress depends exclusively on the current strain. This graph tracks stress versus strain for an elastic material. The curve rises under load and snaps immediately back to the zero origin. The material retains no physical history. In a purely viscous system, applied forces cause permanent, irreversible deformation. The structure is lost and the graph flatlines, reflecting a total lack of recovery. Viscoelasticity combines these behaviors. The material recovers its shape while retaining a physical trace of the deformation. The graph loops back on itself, forming a hysteresis loop. The area inside that loop represents structural history. The kernel function, g times t minus tau, governs this loop. The time delay variable dictates the rate at which the material relaxes, or forgets, the deformation. The slower the decay of this kernel function, the longer physical memory persists within the material. We see this time-delayed recovery in collagen, polymers, and brain matter. They all possess the capacity to store structural history. This baseline viscoelastic hysteresis prevents the brain from instantly forgetting every stimulus or permanently deforming under the weight of sensory load. As biological complexity increases, tissues act less like solid blocks and more like interconnected webs. This is network viscoelasticity. The system recovers from disturbances by shifting its internal connectivity to absorb and distribute the force. A memory unit can be defined as the ratio of internal connectivity to external connectivity. When this ratio exceeds 1, a distinct cluster isolates itself from the background. This stabilized cluster is a coherence domain, the fundamental architecture of a discrete memory trace.
These domains are organized by a hierarchy of connections. Anatomical structural bonds provide the base level of persistence. Functional and resonance bonds build upon that, utilizing active neural assemblies and oscillatory coupling across brain regions. Even transient thoughts are temporary coherence domains, held together by weak probabilistic bonds. Biological memory structures, from single cells to complex thoughts, are coherence domains recovering dynamically from systemic disturbances. In the human brain, these properties are not distributed evenly. It is a highly heterogeneous mechanical environment. Magnetic resonance elastography maps these differences. The data reveals distinct variations in stiffness and compliance across deep brain structures. The primary sensory cortex is physically structured for low latency input. The hippocampus, by contrast, is more compliant and plastic, allowing for rapid thematic binding. The prefrontal cortex features rigid, long-range connectivity. Its physical architecture is designed for long relaxation times, which supports the maintenance of executive control. We define effective viscoelasticity as the composite of tissue mechanics, anatomical connectivity, and dynamic electrochemical activity. In this model, neuroanatomy maps a precise topographical gradient of mechanical memory timescales, rather than simple spatial functional zones. The Brain Kinematics Model hypothesizes that different types of cognitive processing, or mentation, must utilize specific viscoelastic gradients. Think of raw electrochemical data as a neural strain flow navigating the resistance of these networks. An episodic memory follows a specific path. Strain flow moves from sensory input regions into the highly compliant hippocampus for initial theme generation. That memory eventually stabilizes in the association cortex, a region mechanically suited for long-term functional persistence. Action selection follows a different gradient. The flow originates in the prefrontal cortex and routes downward through the basal ganglia and into the motor cortex. This process requires the repetitive, reinforcement-stabilized architecture of the basal ganglia to execute a motor command accurately. Information physically flows from fluid sensory reception into temporary viscoelastic binding and eventually into stable structural meaning. The qualitative nature of a thought is dictated by the specific mechanical gradient the neural strain flow crosses. This physical framing explains the mechanical necessity of forgetting. With zero relaxation time, every input is permanently retained. Under continuous load, internal tension causes the structure to violently buckle and warp. An infinite memory brain would accumulate neural strain endlessly, destabilizing the network. The same viscoelastic relaxation that allows the brain to adapt to new stimuli also results in the gradual fading of old data. Forgetting is a mandatory mechanical relaxation mechanism that prevents catastrophic network failure. We see a hierarchy, from a single molecular hysteresis loop up to functional network bonds. These bonds organize into macroscopic brain regions, each with a distinct viscoelastic signature and decay rate. Electrochemical phase waves lock these regions together into stable configurations. The Brain Kinematics Model views consciousness as a global coherence domain, where disparate regional signals are dynamically stabilized into a single state. Human cognition is therefore an extension of the same physical property that governs all matter: path dependence.